In this video, you'll learn how to interpret the performance of visual AI models in LandingLens for Snowflake. Specifically, you'll learn how to compare multiple binary classification models using the model metrics, the detailed performance report, the heat map overlay, and evaluation sets. Here we go. I'm working in LandingLens for Snowflake, and I'm inside a project named Pneumonia with Uploaded Labeled Images. In a previous video, we trained 4 models, 1 using fast training and 3 using custom training. Now it's time to interpret the results. Let me start by saying that it is not realistic to create a medical imaging model based on 100 total images. We will use the results of the 100 image experiments to decide which experiments to scale up with more images. First, let's look at the F1 scores for the train, dev, and test splits in the summary table on the Models tab. The F1 score is a common overall measure of model accuracy, which you can learn more about from external sources. The split distribution is 65 images in train, 26 in dev, and 9 in test. So a 98% F1 in the test represents getting 1 of 9 images wrong, and 96% in dev also represents getting 1 image wrong. Therefore, at a high level, I would declare all of these 4 options as roughly equivalent. So now what? Well, second, let's look at the detailed performance report to check if the error was a false positive or a false negative. For this use case, a false negative, not detecting pneumonia when it is present, has more severe consequences for the patient than a false positive. I'll click on the table row for experiment C, then click on the performance report and expand it to full screen. There are actually 3 separate performance reports to look at for the train, dev, and test sets. The test images were not used to train the model, so let's start there. There are 8 correct predictions and 1 misclassification. The misclassification is identified with a red X and happens to be this one in the upper left. The number next to the prediction is the model confidence, 0.86. Notice that for the incorrect prediction, the model confidence is lower than the 8 correct predictions, which are all 0.99 or 1.0. The incorrect prediction is also a false positive, predicting pneumonia when none is present, which we stated earlier has less severe consequences for the patient. Now let's look at the test set for experiment A. This one error is also a false positive. Here, the confidence on the incorrect image is not the lowest in the group. 2 of the normal images were correctly classified as normal with lower confidence than in experiment C. So at this point, I'm favoring models B and C over A, and will mark them with a star to keep track of my work. Allow me to show you another way of navigating to the detailed model performance. From the Build tab, you can also click on the model cards on the right-hand side. Some users may prefer this view of the data, which offers a confusion matrix view and the additional precision and recall metrics that will be familiar to machine learning practitioners. This view can be especially helpful when you have more classes that you want to analyze separately. Clicking View Full Report will take you to the interface with the images and confidence scores that we saw earlier. For the third evaluation, I'll examine the heat maps associated with models B and C. On the Build tab, notice the radio buttons to overlay the ground truth or the predictions from any of the 4 models. With the predictions from experiment B selected, I'll toggle on Heat Map. The heat map answers the question, which pixels in the image contributed most to assigning the image to a class? The colors across yellow, orange, purple, and gray show the degree to which each area contributed to the class being assigned, with yellow being the most impactful. The heat map view also allows the evaluator to assess whether the model is learning the correct things. In the case of chest x-rays, a human radiologist would be looking at the lung area within the rib cage. If the vision model was viewing the images the same way that a human does, the activated regions would all be within the rib cage. I would go one step further and say that normal images require both lungs to be clear, so the activations should be symmetric on both sides, while the pneumonia activations could be more asymmetric. This is an example of applying subject matter expertise to know in advance what you're expecting to see in these heat maps. For experiment B, I don't like how many of the normal images have activations along the armpits and sides and not within the lungs. But in the cases where the model is focused on the lungs, the activations are roughly symmetric. Let's see if the heat map can help us pick a frontrunner between B and C. I'll switch to view experiment C while still filtered on the normal lungs. Model C seems very interested in the central spine area. There are fewer activations in the armpit area, but also fewer activations within the lung lobes. Let's view the pneumonia images. The vast majority of the activations are within the lung area. Compared to Model B, I'm more confident that Model C is focused on the correct pixels within the image, the way that a radiologist would be. Let's do one final evaluation. On the Models tab, there's a space devoted to additional evaluation sets. Luckily, I have more than the original 100 images. I'll select 100 more as an evaluation set to show you the process. Notice that the Add button asks me to select a snapshot. I don't currently have 100 more images in a snapshot to select. To prepare the evaluation set, I'll need to add more images to the project via a Snowflake stage and then create a snapshot from those images. I'll fast forward through that process now, and you can see it explained in another video. Great, I'm back on the Models tab after having imported more images and saved them as a snapshot. Now I can choose Eval 100 as my evaluation set, and I'll add it to the table. After a brief processing pause, you'll see the word Evaluate appear in each row. Go ahead and click that. The text will change, and you'll get a pop-up saying that model evaluation has started. I'll fast forward through the wait so that we can see the numbers pop up. Which one do you think is going to win the evaluation? As you can tell, so far I've put my bets on Model C, but I don't actually know who's going to win this evaluation contest. This is real science. All right, C came in with an F score of 75%. It's a little lower than I thought. A, 66, even lower. Ooh, B at 79. Haha, and fast trading at 80. I didn't even bother to evaluate that one, and it looks like it's doing the best. Again, this is real science. So what additional evaluation options does this open up? Now you're ready to use the powerful Compare Two Models side by side. You'll select one of them as your baseline model and one as your comparison. I'll start by selecting Fast Training and Experiment B. Let me orient you to this chart. This is displayed as a confusion matrix, which is already confusing enough, but notice the two columns for the baseline model and the candidate model. This is all about comparing differences between the two. The first thing I notice in the correct section is that both models predicted 49 of 50 pneumonia cases correctly. I also notice that each model has one false negative, where the patient does have pneumonia, but the prediction is normal. The bigger problem with both models are the false positives, cases where the ground truth is normal, but the prediction is pneumonia. A model like this is going to scare a lot of people into thinking they have a severe illness when they don't. Let's investigate further. I'll click on View, and this will bring up the exact images involved in the misclassification. Note that the fast training baseline model has 19 false positives. Experiment B has 20 false positives, but there are 25 images in this list. That means that the two models are making errors on different images. Although the metrics may look the same, they are different under the hood. On the right-hand side, we see the ground truth and the prediction from the baseline and the candidate model. There are cases where one model is correct and the other is incorrect, and there are cases where both models are incorrect for the same image. I just did this work yesterday, so I mostly remember the training settings, but if more time has passed, it's very useful to click Compare Training Settings to remind yourself about the configuration for each of these models. Exiting this view, I can return to the Models table and select any two other models to put side by side, such as B and C. This is a powerful way to really dig into the small differences between two candidate models as you get closer to the end in your development process. To recap, we looked at 4 different ways of evaluating model performance. First, we compared F1 metrics in the model table. Second, we looked at the detailed performance report and examined the misclassifications and the confidence scores. Third, we overlaid heat maps on the predictions to convince ourselves that the model was looking at the right region of the image. And 4, we added an external evaluation set and calculated all of the metrics on each model against that set. Now you're equipped with multiple methods of understanding model performance in LandingLens on Snowflake.